Now, before we get into discussing the ideal gas law, we need to talk a little bit more about expressing the amount of material, because chemists tend to use different values than physicists. Because we started this semester by learning about mass, and mass is the amount of material. However, chemists tend to use what is called the mole. So, little n is going to be the number of moles. So little m is still mass of the substance. And this m here is going to be the molar mass. And you're going to get the molar mass from the periodic table. So if you look at a periodic table, and so let's use carbon as an example, and it's going to be different for each element. Carbon, you'll see 12.01 written underneath. That is the molar mass, but we do have to be careful here. Molar mass is given on the periodic table in grams per mole. So you need to convert that to kilograms per mole by dividing by 1,000 before you use that in any of our formulas. So let's talk about how a mole is defined. A mole is defined through what we call Avogadro's number. Avogadro's number is equal to 6.02 times 10 to the 23 particles per mole. And particles is a placeholder word here. To have a mole of something is to have 6.02 times 10 to the 23 of that item. So you could use particles, you could use atoms, you could use moles, you could use pencils. As long as you have 6.02 times 10 to the 23 of something, you have a mole of it. So 6.02 times 10 to the 23 pencils is a mole of pencils. 6.02 times 10 to the 23 oxygen atoms is a mole of oxygen atoms. This means that we can find the number of moles if we have the number of particles by dividing by Avogadro's number. So capital N is the number of particles or atoms or pencils or moles, whatever sort of number of things you're counting, and then you divide by Avogadro's number, and that tells you how many moles you have. Another number that we're going to need as we progress through this section is the mass of an individual atom rather than the mass of the substance. You're going to find the mass of an individual atom by taking the molar mass, so what you found up here, and dividing that by Avogadro's number. All of these are things you might see in formulas to express the amount of material that you have. So that's something to keep in mind as you progress through these sections, that it may not just be plain old mass that you're plugging in. Now that we know how to express the amount of material in multiple ways, we can discuss the ideal gas law. Now, because it has the word ideal in it, that means we're making a couple of assumptions. The first, we're going to assume that the gas molecules move randomly in the container. So there isn't some sort of mass motion to the left or to the right, they're moving around randomly. They exert no long-range forces on each other. This can have a small effect on the pressure because the gas molecules are attracted to each other and not pushing on the walls of the container because of that attraction. And number 3, that they are point-like. In other words, they take up a minimal amount of space in the container, which would expect the volume of the container that the particles can move around in. Alright, so our ideal gas law is that pressure times volume is equal to number of moles times the ideal gas constant times temperature. So we're going to use pressure here, in pascals because that is SI units. Volume is going to be in meters cubed. Number of moles is going to be in moles. And temperature here, this is one where it has to be in Kelvin. Now we can discuss this constant. This is the ideal gas constant. And for us, it's going to equal 8.31 joules per mole Kelvin. There are other ideal gas constants out there. A lot of them are just converted into different units based upon what your pressure, volume, and temperature are going to be. There are also some weird ones for different planets, but we're going to use 8.31 joules per mole Kelvin. There is another form of the ideal gas constant. And it looks very similar. We still have pressure times volume, so that hasn't changed. But instead of using number of moles, we're going to use number of particles. And instead of using the ideal gas constant, we're going to use the Boltzmann constant. And then we still have temperature. So the Boltzmann constant here equals 1.38 times 10 to the minus 23 joules per Kelvin. And so we call this the Boltzmann constant. And this is going to come up in another relationship later on in this chapter too.